Hello, welcome back to EEforEveryone, part 11 of the plant light project. Today we're going to talk about the thermal performance of the plant light. We'll set the lamp to full brightness, let it run for a while, then measure the temperature of an LED, the PCB on the LED side centered between two of them, and the temperature of the PCB on the heatsink side. We'll also measure the average temperature of the LED side of the board with an infrared thermometer. We'll be using a thermocouple for most of the measurements. You may notice that this enclosure and mounting hardware just appeared out of nowhere. Yeah, so I would have loved to test this outside of the enclosure because it makes probing the LEDs a lot easier. But I made a bit of a mistake, and that's that the PCB is too thin to stay flat under the mounting pressure required to keep the heatsink from sliding around. So in order to keep the board with the heatsink installed, which we do for this test, I had to put it into the enclosure and screw it down. This bracket on the top is really what is holding the PCB flat, but having the support of the mounting screws helps as well. The combined effect keeps the PCB flat enough to prevent the thermal contact between the heatsink and the PCB from being too poor. In the final assembly of this lamp, some thermal interface material will be added as well, but we will need to take the heatsink off again to make some modifications to improve the design in a future video. Instead of wasting thermal paste by applying it and cleaning it off so I don't make a huge mess during the reworks, I'll just forego the thermal paste for now and we'll come back to this. Our temperatures may be a few degrees higher than they will be after applying the thermal interface material, but the metal-to-metal contact thermal resistance is pretty low. I measured this lamp against one with thermal paste applied, and the LED temperature is within 5 degrees between the two lamps. So let's get the power flowing. With the lamp off, waiting for it to boot. Well, the LEDs are turning on because it was pre-programmed. Now there is a bug. The lamp was in the middle of ramping on. I interrupted the process and then turned off the LEDs. And it's not turning back off. Well, I know a quick way to fix that. Boot sequence began again. Since we set the time, it's not beginning to ramp up. We are consuming 0.6 watts from the wall. Alright, the ambient temperature, as measured by the thermocouple, is 27 degrees Celsius. Okay, taking the IR thermometer. Oh geez. Well, here on the bench we're getting around 28 degrees Celsius. So, it says 28.1. Put that in parentheses so we can keep track of it. Alright, so let's turn on the LEDs. Let's get this going. Let's go into the settings menu, turn on the lamp. You can hear the fan spin up, and the light is at full brightness. I do have a lot of lights on in here, and it's a sunny day, though the blinds are partially drawn. And yep, this lamp is bright. So, I will take my thermocouple and I will slide it into the enclosure and rest it up against one of the LEDs. And we will let this sit for a while and we'll come back. For those who are curious, this is running at 100% brightness. If you can see the display, that comes down to 300 milliamps per channel. Actually, we just measured that not too long ago. Why don't you check out that video and take a look at how we measured the current and how accurate the current regulation is compared to the set point. If I remember correctly, we were around 3% off from the set point. It's not too bad. The lamp's been running for a while. We've come very close to our resting temperature, and well, I'm getting a little impatient. I want some results. So we'll probe a couple LEDs. This one right here showing 63 degrees. We weren't quite on the LED, so don't stare at it directly. These are ridiculously bright. I'm just gonna probe a couple of the LEDs directly. Alright. This red one is around 60 degrees. This green one is around 67, 68. This white one in the middle, maybe 75. Let's take a look at this guy right here. So I'm going to say, on average across the whole array, very near 70 degrees Celsius. It's that's when I'm probing the top of the LEDs. Oh, forgot to measure the wattage. So you got 30 watts from the wall. Alright. The LED temperature was around 70 degrees C on the top. On the PCB right next to one of these LEDs, around, I'll say 65. If we try to get centered between two LEDs, maybe around 55. We have to let that settle out. Then again, the thermal contact could be worse when the heatsink's hanging off on the side. I should put this back in the orientation where it's meant to be used. It is quite warm. So we'll say around 60 when we're further from an LED. So that's what I'm calling the average temperature near the ground plane. And measuring on the heatsink side, yeah, around 32. We'll call it 33 since we're coming up to the actual set point. And so there's IR LEDs on here, but they're a different kind of IR than what an IR thermometer picks up on. So, even so, I'm going to measure it before and after turning off the LEDs. So you got 62 for the average temperature at the bottom of the enclosure. Keep in mind, some of that's the plastic and not necessarily the LEDs or PCB. Woo! Almost dropped it. Boy, am I glad I didn't. So you're getting 70 is the average temperature with the LEDs on. And we'll do that again. Whoa, that actually did change the measurement. So, yeah, off is probably better in this case. We're getting around 56 degrees Celsius is the average temperature of the bottom of the plant light. We're getting around 51. I don't know what I just said before, but I'm pretty sure it wasn't 51. Just doesn't make sense because, well, see, so this is able to dissipate heat. So this should be cooler than the PCB on the heatsink side. I think it said something like 60 before, but yeah, it was around 51. These IR thermometers, I like them, but I consider it more of like a toy than an actual measurement instrument where it gets you pretty close. But if you want a proper temperature measurement, you need a thermocouple or something more accurate that's in direct contact and at the temperature. Let's make some quick math and take a look at what this is telling us. See if I can get it all in frame. It's writing kind of big. So with the, we were seeing 0.6 watts with the LEDs on, we were seeing 30. We know that that switch mode power supply is about 80% efficient. Actually, I think it was, we'll say 85. That was from the previous episode, and that was just recollection, so we'll use 85. So this is the amount of power that the LEDs were seeing. And the temperature rise, we'll say, we'll use that 70 degree number. So that's 70 minus 27. So we know that our thermal resistance is the change in temperature over the change in power, degrees C per watt. Let me pull out my calculator. About 25 watts going to the LEDs. Yeah, so I'm not quite sure what to call this, because normally theta JC would be the junction to case, and theta JA would be the junction to ambient, but I guess we're kind of looking at case to ambient in this case. That's the package of the LED. So I guess we'll call this theta CA. So we're looking at how this heatsink is affecting the thermal performance. Oh, I put that on the wrong side. $70 minus 27, 43. So we got 43 divided by 25 would be 1.72 degrees C per watt. That's not bad. 2 degrees C per watt to go from the LED through the heatsink to the air. There's a lot of thermal resistance there. To draw this as a picture with an electrical analog, so you have the junction, and from the junction there's a thermal resistance to the case. From the case, there's a thermal resistance to the PCB, and from the PCB, there's a thermal resistance to the heatsink, and from the heatsink, there's a thermal resistance to the air. And the sum of all of these resistors is that 1.72 degrees C per watt, which means any length in the chain, any link of the chain cannot have that high of a thermal resistance. Or in other words, there's good thermal contact between the PCB and the heatsink, good thermal contact from the PCB to the LEDs, and this heatsink is doing an adequate job with the airflow it has to dissipate that heat to the air. The short way to say this is that it's a pretty good thermal design. Though, if we really want to crank this brightness up further, we don't have any more headroom. I don't want to run these LEDs much hotter than 70 degrees, and that's where we are. So with the power level we're pumping into the LEDs and this thermal design, we're pretty much at our maximum here, which is a good place to be in my opinion, because that means that between the whole system, the amount of power we're pumping into the LEDs is appropriate for the amount of heat we can dissipate. We don't need to turn down the maximum current level of the LEDs to accommodate the cooling solution, or we're not wasting a bunch of cooling potential on power that we're not able to push through the LEDs. So the system is matched pretty well, at least the way that I've implemented it. Though, all that said, I'd really like to have a temperature sensor on the board, because now we know that if the LED is spinning and the heatsink is mounted properly, if we let the LEDs run at 100% for a length of time, that the LEDs won't overheat, and that's a good thing. But what if someone sticks their finger in the fan, or the fan burns up and stops working, or the heatsink falls off because it was dropped? How would we know? We have no feedback telling us what the temperature is. We have no feedback telling us what the temperature is, and I'd really love to have something like the LM60 on the board, just a few of those interspersed, or even one in the center of the grid of LEDs to monitor the temperature of the plane. Because if we know the difference in temperature between the PCB and the LED, and we know that the chip, the LM60, is approximately the same temperature as the PCB, then we can measure the LED temperature and make sure that we aren't overstressing our LEDs. We aren't getting them too hot. That'd be a good failsafe to have. And I wish that was in this design. So if I were to do this again, if we want to push this lamp harder, get more power dissipated, I think that'd be a good thing to add. Overall, the thermal performance is good. As long as the fan keeps spinning, the LEDs of the plant light should stay nice and cool. Stay tuned for future parts of this series, where we will continue to tweak and tune the design before we call it finished. If you think that LEDs are cool and this video is great, let me know by hitting the like button on this video, subscribing to the channel, and leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Bye!